hope so. So it's going to be quite a long day for you, and you'll be sort of completely fed up with mechanics of materials. But that's how it is. So in the afternoon, it's another story, and the story is called statically indeterminate structures. And this is something which is, of course, very practical, and actually it's not that difficult. So I'll just sort of try to explain just a few concepts. And as we did in the morning, remember that you'll get a question on one of the questions during the examination, during the oral examination, will be exactly this subject, this statically undetermined structures. And then you're supposed to to highlight a few bullets. So I'm not going to give you these bullets explicitly, but just remember that you are supposed to present kind of a short story which replicates what I'm going to talk about. So the first thing is just to define what is statically indeterminate structures. So what is the feature of these structures? Then we look at the simple cases, which is this axially loaded members, extension compression, then shafts in torsion, and then beams in bending. And then it's going to be very actually it's very long exercise session with a lot of problems. But to be honest, this is something which is nice to do. So of course you are welcome to solve this problem, but don't be especially desperate to solve them all, especially two last ones, because they're quite demanding, I'm afraid, and this is something which lies slightly beyond the ambition of this course. So anyway, let's get started. And then of course our literature is this book by Guerre and Godno. It's Mechanics of Materials, and this is this set of exercises. And then first of all, what is this about, this statically indeterminate structures? And the answer is very simple. So in the real life, as you can see from these pictures, we have a lot of what is called redundancies in the structure. So we have a lot of members which are interconnected. And of course, this is something which is absolutely needed in order to secure the strength of the structure. But then we have only 3 equations if we do 2D problems of equilibrium, or we have 6 equations of equilibrium in spatial structures. And then, of course, for example, here in this simple example in the right down corner, you see that we have these 4 elements which are connected all together in this joint below, capital A, and then it is loaded by the weight weight W. And then in this case, we have the forces which are coming through the same point. So we have only 2 equations to find the forces, and then we have as many as 4 components, and each of these components may have have to withstand some force. So here the point is that we are not able to find the forces acting in these members using only the equilibrium equations. So it's very, very simple. And then, of course, if you have this complicated 3D structures in this nice picture, then, of course, you have plenty of elements, you have plenty of constraints, and then the system is not statically determined, and it just means that you are not in a position to find the forces in each and every element using the equilibrium equations. So it's very, very simple. So statically determinate structures, there you find all the forces in the components using equilibrium, and statically indeterminate structures, then you can do it. And in the real life, we always have this high level indeterminacy. Then the very simple example, the next slide. So if we have this beam, so you have here hinged beam, and you have a fixed support and you have a sliding support. Then you set up the free body diagram, you release this beam, and it's exposed to this to the inclined force P. So then if you release this beam, you introduce the horizontal reaction HA, and you introduce two vertical reactions, this RA and RB. And then for this system of forces, if you set up the free body diagram, you have three equations. And fortunately, you have exactly three unknowns, this horizontal force and two vertical forces. So you take, you formulate three equations of equilibrium, and you are done. You find these reactions. And then you can go into the cross sections and find the forces inside the beam. But if you just slightly change the fixation, so if you just say that this point A is not hinged, but it is clamped. So here the difference is that you remember that this hinge support means that this point, it cannot go upwards, it cannot go horizontally, but it may freely rotate. Now, if we say that it's clamped, it just means that we exclude rotation of this cross section A, so it cannot rotate. If it cannot rotate, it means that there is also the moment which prevents this cross section from rotation, and we are immediately in the trouble. So we have the same number of equations. We have only three equations, two sums of forces and one sum of moments, but then we have four unknowns. So we cannot find the forces acting at this beam from the constraints using only equilibrium conditions. And then this is very, very simple. And in the reality, of course, we deal almost every time. We deal with these statically indeterminate structures. So then what to do? How we can come out of this kind of trap? And then, as it's sort of stated here, so we need to use some extra information of the structure or the problem we are going to solve. And then this is something which is related to the division line between mechanics or theoretical mechanics and applied mechanics or mechanics of materials. And the division line is very simple. So then we talk about theoretical mechanics. We just assume that the bodies are absolutely rigid. So they are not there is no possibility for them to be deformed in infinitely small or in a finite amount. They're just dead rigid. And then as soon as we go to the mechanics of materials or to what is called applied mechanics, then we say, no, these elements, these beams and shafts and trusses, they may deform. Of course, they deform in a very small amount in most of the cases. And in our considerations, we'll stick to very small deformations, but they may deform. And then it means that we have on top of this static equilibrium equations, as you can see here, this sum of forces equals 0, sum of moments equals 0. So we, as I say, in 3D formulation, we have only 6 equations. Then, and we may have 100 unknown forces. Then we have what is brought due to this deformations, we have compatibility equations. Then they're also called geometric or kinematic equations, and I'll try to explain it in a moment. So the simplest thing is just to impose zero displacement. But there are some most of the advanced, let's say, ways to formulate it. So then these compatibility equations, they bring into light the geometry. So then the deformations of different members must be coherent with each other. And then the third group of equations is the relation between forces and displacements. And of course, you recognize here in this lower frame, it's a Hooke's law. So we say that the force is, it produces the displacement in accordance with the Hooke's law. And again, in our lecture today, we will be dealing only with these linear elastic materials. Right. So then, in order to make it clear and also to draw your attention to some kind of the gray areas, just let me take a look at this example. So what happens here? So let's say that we have the absolutely rigid, quite heavy bar, it's absolutely rigid. So it's kind of there. It's shown like this. And then it has a weight G, and it is sort of hinged at the left edge here. And of course, it will fall down unless we fix it to the ceiling. And then here we just want to be a bit sort of secured. So we, of course, one of the ropes will suffice. But we say now we just want to be absolutely secure. So we say that we want to put 2 ropes like this. And then as we introduce this structure, then we immediately have to deal with all these sort of 3 types of equations, which have to be sort of solved together. And this is here very clear and very simple example how it is done. So the first thing is that, as in the theoretical mechanics, we have equilibrium. So this is something which is undisputable. We have equilibrium, and in order to set up the equilibrium conditions, we have to present this free body diagram. And this free body diagram is sketched here. And again, I hope it's not that much surprise to you that here in the left edge we have the hinge support. So we have vertical reaction R1, we have horizontal reaction R2, and now we have these 2 ropes. And then as we release this absolutely rigid bar, then we have the force R3 and R4. And then this the weight G acts as shown here. And then you can immediately see that we have this sort of trouble, that we have 4 unknown reaction forces, and we have only 3 equations of equilibrium at our disposal. Sum of the forces in the horizontal direction, sum of the forces in the vertical direction, and sum of the moments with respect to any point in the structure. So then we write the equation of equilibrium in horizontal direction, and it gives us immediately that the R2 equals 0. It's hardly surprising. Then we write the sum of forces in the vertical direction, and I think it's also quite obvious. And then we write the sum of the moments with respect to point O. And in order to kill these 2 forces, R1 and R2, it's reasonable to write the equilibrium equation with respect to point O as sketched here at this point. So then again, we use this sign convention that rotation anticlockwise gives you positive moment, otherwise it's negative. So then, and then of course I did it in the wrong way here. So it's, of course, it's all opposite. I was a little bit in rush. Please just sort of the mark it. So here it's sort of the with minus. So of course the force R3 gives the positive moment. The force R4 gives the positive moment, and this force G gives the negative moment. But never mind, while you'll be doing your exercises, I will change this slide and change the signs. But it's just if you multiply it with -1, it will be okay. Never mind. Now what is sort of important is the compatibility condition. And then this compatibility condition needs to be very, very clearly explained. And the key to understand how this compatibility is formulated is that we assume that the deflections are very, very small. So we, in mechanics of materials, then we put formula equilibrium equations. We assume that the deflections are absolutely absent. So there are no deflections. So we just sketch this bar as absolutely horizontal. And then this is, so it's horizontal here, and it's also horizontal here, so that we have this free body diagram. But then if we talk about compatibility, we say that the deflections are not 0, but are very small. And what is presented in this sort of the number 2, this compatibility, is awfully exaggerated. So in reality, so if you have these ropes of the length, this h, let's say if it's 1 meter, then this delta 3 and delta 4, it will be something like 0.1 millimeter, maybe 1 millimeter, something like this. So they are very, very small. And the physical explanation for this is that we have very high Young's modulus, and if we and relatively small ultimate strength. So because you remember the Young's modulus is order 10 power 11 pascals, and the ultimate stress is something like 10 power 8 pascals. So it's 1,000, 3 orders of magnitude, 4 orders of magnitude difference. So it means that if you have large deformation, the structure will will break down. So these deflections are very small. And then this is what we it's something which is, I understand, is quite confusing, but please see it as it is. So as we say that the deflections are very, very small, then we can say that this point goes strictly down, and this point also goes strictly down. Of course, in the real life, if we allow large deformations, then it's obvious that this element, it will rotate around this point. It will rotate, and then of course it will be this point will travel on the circle of the radius L12, and this point will be traveling on the circle of the radius L concentric with the previous one. So it will be just arcs here and here. But as I say, we say that the deflections are very, very small. So then we say that yes, of course, there is some sort of the horizontal component of displacement to this point. It doesn't go strictly downwards, but we neglect it. And likewise, this point, it also, strictly speaking, has some sort of the deflection in the horizontal direction, but we also neglect it. So we say that both these points, they go strictly downwards. And then it dramatically simplifies the formulation of the problem, because now we have this large triangle, and we have a small triangle, and here we have this length L, and here we have length L12, and then if these are two triangles, then it cannot be other way than to say that our delta 4 equals twice delta 3. And before I go any further, I just want to get your feedback. Do you really see that's like this? Because I can't believe that you agree. I'm sure that you should come up with some sort of a skeptical comments. Some questions, because this is very important thing which is used in mechanics of materials. So we assume that there are some deformations, but these deformations are very, very small, so that we may simplify pictures like this.
Maybe R4 should keep the beam up.
Pardon?
I'm just being skeptical. Shouldn't R4 keep the beam upwards so it doesn't deflect downwards?
Yes, so in principle, of course, these forces R4 and R3, they prevent this beam from moving downwards, of course. But due to this compliance of these two ropes, let's say, so that these are two kind of strings or ropes, so they are quite stiff, but they are not infinitely stiff. So we have tiny little bit of displacement downwards of this point there, the force R4 acting, and equally tiny little displacement downwards of the point there force R3 is acting, due to this weight of this horizontal bar. So this is the fundamental difference between this, as I say, theoretical mechanics or mechanics of rigid bodies and applied mechanics or mechanics of materials. In the mechanics of materials, we allow for deformations, but we say that these deformations are very, very small. But they must be coherent with each other. They must be coherent with each other. So we cannot sort of say that the deflection delta 3 is absolutely independent upon deflection delta 4. Because this rigid bar, it was sort of straight before the deformation, dead horizontal, and after deformation, this stiff and heavy horizontal bar, it remains straight, but it sort of it goes downwards. And you see the way I have shown here, it looks like it has become longer, right? Because it's sort of this delta 4 downwards and delta 3 downwards. But the thing is that we ignore this thing. We just say that these points, they go, of course, they have some horizontal deflections, these points, their forces are acting, R3 and R4. But these horizontal deflections are negligible. We neglect it. Otherwise, we cannot do the compatibility in this simple way. But this is something which has been used for 300 years. All the structures, and probably intuitively even before that. It's something which is sort of this is how the engineering sort of matured, using these assumptions.
I have another thing. Is it done this way because the deflection is bigger than if it would rotate around the point on the left?
So this is done because the deflections are so small that we can say that it's not actually rotation, so it's just going downwards. So mathematically, what happens, but probably I'm not sure that it will be more sort of the explanations and confusing. Mathematically, you know that if you have cosine function, and then if the argument is very small, then you can say that cosine theta equals 1. And then if you have a sine function or very small argument, then you can say that sine function equals the argument. So sine x equals x, and cosine x equals 1 if x very, very small. So from the viewpoint of mathematics, this is what is done here. And it works all the time. So there is a lot of inconsistencies here, and I have to be to highlight them fair, but it's something which is sort of checked thousands and thousands and thousands times. So the first thing is that the equilibrium equations, these ones, they are written in the framework of mechanics of the rigid body. So then we sketch this free body diagram. We ignore deflections. We just say that this bar is absolutely dead horizontal. And then we write these equations. Then if we go, and then we are stuck with this sort of the indeterminacy, so we don't have enough equations. We cannot find reaction forces. We cannot design the structure, but we need to design the structure. We need to design these ropes to ensure that this bar doesn't fall down. And then in order to do it, we say we allow for deformations, but these deformations are very small. So small that this point goes downwards, and this point also goes downwards, so that we have this relation between displacements of the point 3 and point 4. And then if we sort of kind of survive with this, then we introduce the third group of relations, and this is what is called Hooke's law. So this is just the relation between the force and displacement. Because of course this displacement is produced because of the action of the force. And here this is action and anti-action. So this force R3, I have shown it upwards because this is a force which acts from the rope onto this bar. So that's why it supports this. But this horizontal bar, it pulls this thread or this rope down. And that's why it goes down. And force of action equals force of counteraction. And then we immediately have this formula for the Hooke's law. So the deflection delta free is this force R3 times the height, this height, divided with the stiffness of the string EA. And this delta 4 is like this. So it's R4, again the same height, and then stiffness the same, for simplicity, just identical strings. It's the stiffness EA. And then this gives us what we need, because now we can count the equations. So we have this moment equation where we have R3 and R4. Then we introduce this equation, but at first glance it doesn't make our life easier because we introduce two unknown displacements. So now we have 4 unknowns and 2 equations. But then we close the system writing the Hooke's law, which gives us the 2 additional equations. So now what we have the system of 4 equations. The first equation is the equilibrium with respect to the moments, this one. The second equation is compatibility equation. And the third equation is the Hooke's law written twice, for one string and for another string. And then if we return to something, if we just go back to the slides, and then if we go, for example, for this system, then it will be the same story, because these elements, they all will deform very, very slightly, but they will deform. But the key point is that they were connected at point A before this weight was acting, and they remain connected at this point A after the force is applied. And then this will give you exactly the requested number of compatibility conditions. So here in this case, in this case, we have 2 elements, and we have sort of the 1 compatibility condition. And in the case which I have shown from the slides here, we have compatibility between displacement of this point. This point belongs to this rod, this rod, this rod, and this rod. And they're connected before, and they are connected after. So then it gives you all the requested amount of equations, but again it blows up, because you remember that for equilibrium we have only 6 equations. In plane structure we have only 3 equations, but number of interconnected elements may be thousands. So then the vast majority of these equations are equations of compatibility. Then we do the statically undetermined structures. And then so now this is, so if these concepts, if you can survive with these concepts, and remember you are supposed to explain it convincingly in the exam in 3 weeks time. So then what we do, we have just to solve the system. So we have 4 equations, 1, 2, 3, 4, with 4 unknowns. And what we do, we combine equations 2 and equations 3, the Hooke's law and compatibility. And so we just plug here delta 4 like this and delta 3 like this. And then after canceling out, here it's all simple because the stiffnesses are the same and these heights are the same. we have the relation between forces R4 and R3. So it's just like this. Then we recall this equation number 1, which is still to be sort of solved, used. And then we just plug here, instead of R4, we plug twice R3, and we cancel L because L stands in each of these terms. And then we say, okay, now that's very simple. We have this R3 is one of the 5 G5, and then R4 is twice R3. It's let's say 0.4 G. And then we also have to find the reaction R1. And for this purpose, we use this not yet used equation for sum of the forces in the vertical direction. And then we find that our R1 is 2G divided by 5. So this is how the problem is solved. Any questions?
I have a question.
Yes, please, yes.
In the second part, compatibility,
Mm-hmm.
are you just supposed to logically find out the deformations or deflection?
Yes. So here, you know, in principle, I wonder if Jorn Kepler told you about it, but the truth is that the mechanics of materials is a science of common sense. So here you just use your common sense, and then I think it's not it's not a rocket science to say that this point goes downwards, and we may neglect horizontal deflection, and this point goes downwards, and we may neglect horizontal deflection. So this is your common sense, yes. And I think I guess there was one more question from somebody else. No? Oh, good. So then it seems like I have convinced you with this kind of approach. But please remember, and this is something which you really sort of supposed to know very, very clearly, that then we go for the statically determined systems. Then we do only equilibrium. So free body diagram tells us the whole story. We are able to find all reactions and all the internal forces using exclusively free body diagram. But in the real life, we have the systems which are multiply statically undetermined, and then it means that we have to use compatibility conditions and use the Hooke's law, which relates for forces in displacement. So this is just the three cornerstones, so to say, in solving problems in mechanics of materials: equilibrium, compatibility, and Hooke's law. Then we move on with the slides, and then this is more or less the similar formulation. So what happens here, but here it's a little bit simpler, because what happens here is that we have this the cylinder, the hollow cylinder made of something. What is it? Just it's tube. It's copper tube. And inside this copper tube, we put the steel cylinder, the solid cylinder. And they are manufactured so that you have some gap between them, and you put this kind of the lid on top, and you press it downwards. So this is what happens. So you have this lid, and you apply the force onto this lid, and then this lid distributes the force between the brass, the copper tube, and the steel cylinder, so that we ensure equilibrium like this. So now the point is how this total force P, this external force, how it is distributed between the cylinder made of steel and the tube, outer tube made of brass. And here it's exactly the same story, but it's a little bit simpler. What we say is that we have static equilibrium, so the external force must be balanced by the sum of the force in the steel cylinder and in the copper tube. And again, we have this challenge, but we have only one equation. We can't write any more equations. It's only one equation, but we have two unknowns. And then here we have to do the same, so to the logical step, we have to introduce the compatibility. But here there are no tricks. It's sort of the straightforward that no matter how, but of course here we suppose that this lead is infinitely stiff. So this lead, this upper lead, cannot deform. So then there is no other way except for saying that the deflection downwards of the tube must be exactly the same as deflection downwards of the cylinder. So they must go down in exactly the same amount. So this is the condition, compatibility condition. And then the Hooke's law, again, we recognize it. So here we have the same length, different forces and different stiffnesses. And then you just plug, just as I showed you in the previous example, you just plug these displacements into compatibility condition, find relation between these forces, and then plug it into the equilibrium equation, and you end up with this answer. So the forces are distributed in accordance to the stiffnesses, like this. Any questions about this thing? Here it's simpler, of course, than in the previous example, because as we already discussed, the tricky thing is to write the compatibility condition. But here compatibility is absolutely obvious. So they must have the same shortening, the tube and the cylinder, right? No questions about it? Good. So now we are done with, and of course you can imagine that there are hundreds and hundreds problems in which we employ these things for the members in the axial extensional compression. So next thing is the torsion. And torsion is very, very similar to the axial deformation, even graphically, because when we show the forces, we have these simple errors. If we have torques or torsional moments, we just use this sort of the nickname. So this is just double arrow. Like this, and like this. But the structure is the same. You see, we have this the same composition, but now the difference is that this structure is exposed to the torque, so that we have this lead is now kind of the welded or glued to this cylinder inside and the tube outside, so that we apply the torque. And then we know for sure that the rotation angle for the cylinder is exactly the same as for the outer tube. So then we write this equation of static equilibrium, and then we write the compatibility equation, which is also the same, that the angles are the same. And then we write the Hooke's law. And Hooke's law for torsion looks as a twin brother of the Hooke's law for extension compression, because in extension, just let me go here, you see you have elongation and you have force. So you apply the force and you have change in length. In torsion, you have angle of rotation and you have torque. And again, so if you do like this, then the force is related to displacement. If you do like this, then the moment torque is related to the angle of rotation. And then, of course, it's proportional to the length here, and length is here, of course, it's the same. And then the difference, at first glance, dramatic difference, but in reality, there is no difference. So here we have this A E, and here we have GI. So then the product AE, it's called stiffness in extension compression. And here the product GI, it is called stiffness in torsion. Stiffness in torsion. So that if this quantity is large, then it's very strong resistance to the torsion. If it's relatively small, then it's to the more compliant. But the interesting thing is that, as you can see, so here this distribution of the forces is proportional to the stiffness in extension compression. These things, L is gone. And then here it's actually it's the same formula, because the distribution of the torque is proportional also to the relation between torsional stiffnesses of these two components. So it's something which is, they resemble each other very much. Any questions about it? No? Okay. So probably you are probably just tired. So then we skip this example, and then we go for the beams for bending, but probably we might have a short break. I think it's more or less about the right time, so it's almost 45 minutes. So if we say that we resume, well, so if we say that we resume at 20 minutes past 1, so in 8 minutes, I think it will be enough for you to take a breath, and then we'll consider bending. And it's better to have some sort of interval before we go to these things. Yeah, so now let's take a break until 1:20. Let's move on. And first thing is that I use this break in order to to correct this equation. You see that now it's all fine. We have moments produced by the forces R3 and R4 positive, anti-clockwise, and the moment produced by the weight negative with respect to point O. And of course, this is something, this page I will upload in Moodle. So then there will be no confusion, of course. But just I would like to ask, maybe you you still have some sort of the concerns, or maybe you just want some extra motivations. I would probably need to explain it a little bit better, this way to do of putting down the compatibility condition in this case. Or you are quite happy with this and you think you are able to convince us when we do the exam that it's going to be like this.
Maybe go through the extra example.
One more example.
Sorry?
Well, you mean to come up with one more example?
No, from the torsional loaded members.
Okay. So this is, it's not the issue. This is just how I sort of jump from this to this. Right? So you just wanted me to give more details about this problem or another example with torsion?
Yes, please. Both, maybe.
Well, so here then we consider this example. We just say that we have the same setup as here. So we have this cylinder, steel cylinder inside, and this copper tube outside. And then we put the lid on top of this. And instead of applying the force, we apply the moment. And of course, then we do so, we assume that we have kind of the welded this cylinder and this tube to the slit. And then as we introduce this external torque, then the thing is that this torque must be balanced by the torque in the tube and the copper tube and torque in the steel cylinder. So then we just write the sum of the equilibrium of moments, and then it's sort of actually this is a lead, and it lead at one side is loaded by this torque, and from the other side it's loaded by two moments or two torques, one from tube, another from the cylinder. And then we see that we have this the too many unknowns and not sufficient number of equations. And then the next logical step is that due to the welding of this lead to both these guys, to the cylinder and to the tube, they must rotate on exactly the same angle. So their rotation is in agreement with each other. And here just that these rotations are the same. So these angles are the same. And then we say the third component here is this Hooke's law. And the Hooke's law for the torsion is written like this. And I sort of spent some time, so I'm not going to return to this again. But the thing is that the Hooke's law for torsion is amazingly similar to the Hooke's law in extension compression. So we have this formula. And then if we take these things and substitute here, then we find relation between Ts and Tc. And then if we substitute it here, then we solve it for find Tc and Ts. So this is the first case with torsion. And then another case, another point here. So this is now we have a step shaft. We have a shaft of the stiffness, this GIP1 and GIP2. And then it's sort of welded. So it's two shafts. And then they are welded at the left end and at the right end. And it's exposed to this single torque acting here. Then what happens is that we have the torque produced which acts here, and we have torque which acts here, and they together they balance the external torque. So we have the same story. We have the equilibrium condition saying that the torque in this cross-section plus the torque at this cross-section must balance this torque. Make sense?
Yeah, I think so.
So now we say we have this static indeterminacy. We have one equation with two unknowns. What we do next? Next we say, aha, our shaft is actually welded here and welded here. It means that no matter what is the magnitude of this torque, there is no rotation of this cross-section with respect to this cross-section. So in other words, rotation angle here must be 0. Make sense? So we measure rotation angle with respect to this left edge. So at this left edge, we count the rotation angle. Then since it is welded here and it's welded here, it may rotate in different sort of direction, clockwise or anti-clockwise along the length. But as we arrive at this cross-section, the relative rotation of this cross-section with respect to this cross-section must be 0.
Okay.
So now this is compatibility equation. We discussed this static equation for the equilibrium of the moments. Then the compatibility equation is that angle here must be 0. And now we do the last step. We have to use the Hooke's law. We have to use this torsional moment rotation relation. And actually these are these formulas. So we have just to apply this formula in a clever way. So what we say is that we have the rotation of this cross-section with respect to this is the sum of 3 ingredients. The first ingredient is rotation of this cross-section with respect to this one. The second component, which adds, is a rotation of this cross-section with respect to this one. And the last component is rotation of this cross-section with respect to this one. So we say that rotation of the element 1 plus rotation of the element 2 plus rotation of the element 3 is 0. And then for each of these 3 rotations, we use this formula. But for each component, for this component, this component, and this component, we have to plug its own parameters. For example, for this component, the length is A, the rotation stiffness is this one, and the torque is, let's say, torque left. So this is the rotation angle of this cross-section with respect to this one. Then we come to this element, and here we have the action of the same torque, but we have change in the stiffness. So the second ingredient will be rotation torque here, multiplied by the same length and divided with the rotation stiffness of this element. So we put them together. Then as we go here, the rotation now is different. Rotation is a difference between torque here and torque here. But then the other components of the formula are the same. So we have the length here and this stiffness. And so they say that angle here plus angle here plus angle here gives you 0. And this is the equation which gives you a relation between these two moments. And then you sort of write the equilibrium equation and solve the problem. Yeah, and I understand it's a bit difficult to sort of to perceive it sort of on the like this, but I mean it will. I can write this this solution and upload it as well. It will take me something like 10 minutes just to write and then to go to scan and then to upload it. So it's no problem. But the idea basically is the same as in a previous example. The idea is just to employ 3 groups of equations: the equilibrium, compatibility, and Hooke's law. Yeah, so should we move on to the beam, or maybe there are some more questions about this and also about this, maybe? No. Okay. So now let's sort of yeah, and I will then you start solving your problems in this sort of from the exercises. I will just upload solution of this problem. So it's very simple. So now we go to the bending, and then of course in bending it's really something which we have a lot of this redundancies. We have a lot of the constraints of displacement. So the simple example is just if you just imagine that you have a a rail lying on the slippers, and you have a lot of slippers, right? So then, and the train applies this transverse force, and then you have the huge redundancy. So you have much more reaction forces than you have equations of equilibrium. So then, how we do it? Then there are two methods, and historically, it's fair to begin with the second one, solving a differential equation for deflections of the beam and use boundary conditions. So this is how it was sort of how it all started. But as soon as you have these solutions of differential equations already available, you just sort of compose kind of the table, which you use just with answers already available. Because if you solve these differential equations once, you can use its solution as many times as you like. And this is, I think, it's called Appendix G in this book by Mechanics of Materials. There, all these solutions are accumulated. So then, and it's way more practical to do this superposition. So here, Johnny here, but I'll also mention it. This is solving differential equation, but it's very cumbersome, and in principle, there is no need to do it once you have these tables. So then, but the logic here is very important to sort of follow. So the logic is that we have here this system, and then we immediately see that we have as many as 5 unknown reactions. So we have this 2 forces and a moment in this clamped edge, and then we have this sliding support. So we have here vertical force, and here we also have vertical force. So all in all, we have 5 unknowns, and we have only 3 equilibrium equations. Some of the forces horizontal direction, vertical direction, and some of the moments. So we have redundancy, which is equal to. So this redundancy is the missing equations. So we have 5 unknowns, and we have only 3 equations. So we need to come up with 2 extra equations. And I hope it makes sense. So we have to formulate equations to complete the system, to close the system, and then it means that we have to come up with the 2 compatibility equations. And then the way to obtain these compatibility equations is very simple. Just you see what happens is that we say that we release our structure at the point B, so that instead of this fixation, we apply the force, this RBY. Likewise, we throw away this support, and instead of this support, we apply this blue force RCY. So now we have the cantilever beam, which is statically determined, because now we have this moment and 2 reaction forces. They can be found from the equilibrium equations if we know this force at point B and this force at point C. So now we replaced the statically indeterminate system to statically determined, but we need to find these reaction forces. Does that make sense?
I don't quite get it.
So now we go to the next logical step, and the logical step is what is the relation. So this is what I told you. So we have this 2 degrees of indeterminacy, and then now we come to the statically determined system. So what we do is we just look at this picture below, and then we see that, and we don't know the forces R, B, and RC. We don't know these forces, but we want to sort of find the forces which make this system be identical to this. And then in order to make them identical, we have to say that the displacement of point B in this system must be 0. And displacement of point C in this system also must be 0. So this is, again, I hope it calls a ring. So this is the same story as before. We just say that we introduce compatibility conditions. We just say that in this system, the forces RB and RC are in the amount which ensure that this point doesn't move upwards and doesn't move downwards, and this point also doesn't move upwards and doesn't move downwards. So that then we introduce these two forces, we immediately introduce conditions that displacement to this point must be 0 and displacement to this point must be 0. Questions? Okay, we move on. Then first thing is we have these three red forces, and we have three equations. So we write these static equilibrium conditions, but it's not of much help because these forces are still not known. And now we come to the very simple statement. We just have to ensure this compatibility condition that the displacement of point B is 0 and displacement of point C is 0. And then we say that the displacement of point B, of this point, is produced by the force, this Q. It's probably it's better just to begin with this. So now we introduce the superposition of these three active forces, because these red arrows, they are reactive forces, but active forces are this Q and this RB and RC. So then we take a look at this picture. So we ignore these two forces, we have only distributed load Q. Then due to this action of the distributed load, for force will be some displacement of point B downwards and some displacement of point C also downwards. Then we say we introduce only this force here. And then this force, obviously, it will also introduce the displacement at point B and displacement at point C. And then the last case is that we have this force acting only at point C, and then it's the same story. This force will introduce displacement at point C and displacement at point B. And now we say that the displacement of point B, which is superposition of displacements due to case 2, due to case 5, and due to case 4, it must be 0. And then I write it, this I already I put here pluses because these deltas, they will be negative. Sorry, this will be negative, and this will be positive because I have this direction of y, but this is what we have in the tables. So the displacements go with their signs. And then also we have the displacement in point C, which is the contribution of loading case this. It will be with minus downwards. And then contribution of the loading case 5, it will be definitely upwards. And this contribution, it will be also upwards. So then we have these compatibility equations. So there is no rush, just please take a look at these things and do you understand it? So what happens, so what we are doing here, what is the logic? And if you have questions, just please ask, because it's also it's sort of the afternoon and we had this stress concentration stuff, so you're a little bit tired. No questions. Okay, but probably it will be some questions later on. You are most welcome to.
I do have a question, actually.
Yes, yes, please. Yes.
I'm going to be absolutely honest. I don't quite understand where so 2, 5, and 4, those boxes. What's the difference? What are you changing in terms of the forces in both directions?
Yeah. So you see, the thing is that in reality we have these 3 forces acting simultaneously. We have this force Q, force RB, and force RC, which are acting all together, and then they're acting in a manner that displacement of point B is 0 and displacement of point C is 0. So this is what we have. Now we come to the very important logical step. We say that we have the superposition of these 3 loading cases. So first, we take only the loading case due to this distributed force, capital Q. And this is the picture. And for some reasons, it's called number 2. So here we say that we ignore the existence of the force at point B and the force at point C. We have only force Q, and then this force Q will obviously produce displacement of point B and displacement of point C. And these displacements, if you look at the direction of y-axis, they will be negative, because here we have no doubts that due to this force Q, this point B will go downwards and point C will go downwards in certain amount. And we are able to find this amount in which these points will go down. Then we say, okay, now we take only force RB, only this force, as if this guy and this guy are absent. And then due to action of this force, of course, point B will go upwards. It's common sense. And point C will also go upwards. And again, we are able, taking the tables, find the amount in which these displacements are developed, depending upon the value of this force, because of course these displacements, they will be proportional to this force, and this force is yet unknown. And then case 4, we forget about existence of this Q and this RB, and we look at the deformation of this beam due to the action of this force RC, which is of course brings point C up and point B also up. And then we say that the total displacement of point B must be 0, and the total displacement of point C also must be 0. And then we have these 2 equations, and they're in fact compatibility equations, because it means that the displacement for point B must comply with the constraint that it must be 0. Any better?
Yeah, that's good. Thank you.
More questions? Yeah, please.
Yeah, so is it correct to understand that you are substituting the forces with deflections?
So you see more precisely, the deflections are proportional to the forces, right? So this is the Hooke's law. And then, but this is what will be shown in the next slide. So then we just take the tables, and then we write the formula for this delta B5 and delta B 4, delta C5 and delta C4, they will contain the magnitudes of these forces as unknowns.
But in the example of the hanging beam with the wires, you use the compatibility equations to find the forces based on deformation.
Yeah, but here deformation is 0. So this is the point, because here in this example we just say that here this point can't move upwards, it can't move downwards, right?
So how can we say that? Is it just because it is an immovable material?
Yes. So this is something which is seen a priori. So we just say, so this point is sort of the hinged, and then you exclude any deformation in vertical direction.
Right.
So this is something which is its essence of the problem formulation. So this displacement is 0 and this displacement is 0. More questions or comments, please don't hesitate. I mean, so we are after understanding.
Just to be completely sure, superposition, that means putting different forces together?
The superposition means that the forces, they produce displacements. And then if you take these three forces and put them together, they will produce the displacement at point B and point C. But the result of the action of these forces together is the superposition of results of these forces acting one by one.
Right.
So if you have three forces acting together, you can say that the end result is the sum of the actions of these forces one by one, independently upon each other. And this is exactly what is called superposition. Make sense? So this is exactly what is written here. So in this picture, you have the three forces acting simultaneously. And simultaneous action of these forces must ensure that point B has zero displacement and point C has zero displacement. So now here what I do, I just sort of introduce superposition, and I say that point B is sort of the we will definitely deflect due to the action of force Q, due to the action of force RB, and due to the action of force RC. But if you put them together, it must be zero, because as they are acting simultaneously, it must be zero. Is it okay? Maybe more questions about it? Okay, so probably let's just take the next step. And the next step is this table. But actually what happens is this table, in this table is just it's sort of the plug and play. So what we do, we just take this book by Timoshenko, by Gere, but we may take any other textbook on mechanics of materials. And then in this texts, we have the appendices, and one of the appendices gives the story, and it gives you the answers. So if you have, so it just you take the book, open the page in this appendix, find this picture, and then you immediately see that if you have this force distributed between A and B, then the displacement of this point B is like this, with minus, and of course it means that this point goes downwards. And for the point C, the displacement is like this. And this has been done by some clever people 100 years ago, or maybe 150 years ago. So there is no reason to doubt that this is the displacements. Then you browse your table and you find this picture. And you say, aha, this is exactly what I need. And then again, you look into the table, and then you see that if you have a force acting here, then you have this formula, and you could be a little bit confused because here if you take the table, you have this letter P, because the table is formulated with the force here designated as P. But in our case, this force is not P, but RBY. And we, again, if we take a look at point C from the same table, then it's going to be like this. And here it's all familiar, except for the P, and P is RBY. And then again, you take the next page, and then you find this one. And then again, for this setup, you immediately find this formula. It's plug and play from the table and this formula. But in order to use this formula in our case, we have to put here instead of P, this force. So in here and here, we substitute instead of P, RCY here and RCY here. And then it gives me the ingredients here. Because this, and this, now this as it is, this with the P replaced by RB, and this with P replaced by RC. And in this formula, also this one, here with RB and here with RC. Make sense? I hope it is. I hope it does. I hope it does. And then we just sort of plug these things, and then this is what I sort of explain. Try to explain that now instead of P, here we put this guy, and instead of P here we put this guy. And then we obtain a system of two equations with respect to these two unknowns, RBY and RCY. And we solve this system, and we've got the answer. So this is a key point in this method of superposition. So we just sort of take the table and combine the data from the table in a smart way. Then you remember it's not completely end of the story, because we have found these redundant unknowns, but we still have these guys, this moment and these two forces, which we have to find. But it's very simple. We just return to this static equilibrium. Now we know this forces RBY and RCY, and we immediately write these equations, and they find this force RAY and this moment MA, just like this. And then now we have found everything, and then we can easily plot the deflection of the beam. And here, of course, it's very much exaggerated, but you see the scaling, because here it's 0.5, 1, and 2, and here it's just 0.5, 0.004. So it's very, very small displacements. But that's exactly what I mentioned to you, that displacements are very, very small. But then the displacement at point B is dead zero, of course. And the displacement at point C is also zero. So the problem is solved. Before we go further, before you'll be completely sort of confused, just take a look at this. Yes, I browse it again. So we have this redundant unknowns, and we introduce the additional equations where displacement here must be zero and displacement here must be zero. So this is our static equilibrium, and this is our key ideas. So we say that this point must have displacement equals zero, and this point also must have the displacement equals zero. And in order to do it, we just take the table, standard case, and combine these things in order to find these forces from this system of equations.
Okay,
Yes.
quick, sorry.
Yes, yes. Eric?
How do you determine the redundant forces? In like, could it be RAY and RBY as well?
It's a very good question. Yes, yes, it's absolutely up to you. So you just sort of include that you have two redundancies, and which ones you sort of identify as redundancies, it's within your discretion. You can do it. You can say that you have RAY and MA as redundancies. But then, of course, you have to look up another table. So in other cases, in other simple cases, right? Because if you, for example, if you say that your redundancies, probably it's better to show it here. So if you say that your redundancies are MA and RAY, this guy and this guy, then the additional conditions will be that rotation here must be zero, because in reality it's a clamped point. And vertical displacement at this point also must be zero. You can take MA and RB, this pair. Then you say that displacement here must be zero and rotation here must be zero. So it's, but again, this is something which comes with kind of the intuition. So you just want to obtain the answer as fast as possible, and then you just see what would be the easiest setup. Because the tables, they are, for example, in Gere book, there are very few sort of the cases, and then you just probably you do this, you choose your redundancies in order to match what you have to your disposal as these sort of the standard cases. But it's a technical question. But you are right. You can. There is multiple choice.
I have a question as well. Maybe it's just like in general, but the compatibility equations, would they often be zero because of the fact that the original structure is kind of locked?
Yes, true. So the most natural formulation of this compatibility equation is just to say that displacement is zero. You're absolutely right. Yes.
Okay.
I have a question as well. I have a little bit of a hard time figuring out where you get the equations for the displacements Could you explain how you get them?
How I get this?
Yes.
This? Oh, it's a long story. It's a long story, and this is actually what will it will follow up. So this is something which I just sort of it's in the subsequent slides. It's here. But before we go to this, and you'll be completely sort of shocked. Maybe I accept your question and I will give you answer just a bit later. But maybe there are more questions.
Okay.
Please don't hesitate. Okay, but probably will be some questions later on. Then you are most welcome to ask, of course. So now it's a very, very good question. So how on earth we find, or not we, but this sort of the people who set up these tables, and I say these tables are very, very old. I would say that it's 150 years old for sure, or maybe even 200 years old. So how did these engineers, so very sort of educated engineers, how they come up with this formula? And it's very simple. The answer is they integrated differential equations for beam deflection. So that's how it works. Because we have the, and I think here I just, it's this are not mine slides, so this is why I have to do the, and just, where is this, why he didn't put it? Yeah, but probably you remember you're on Kepler, because that you have the moment, bending moment, and the bending moment is related to the curvature of the beam. So what we have is that the second derivative of displacement multiplied with the bending stiffness equals the bending moment. So then what you need to do, you need to double integrate this differential equation depending upon the type of loading. So you have the formula for the moment, you integrate it twice, you find two, you have two integration constants, and then you take this as two integration constants from the boundary conditions. So, and then you do it once and for all. So this is how these things are done. And then just let us look here, but I'm afraid you'll be really lost with this, because what happens is that we have here in this beam, we have two sections. We have the span of the beam between point A and B, and we have a span of the beam from point B to point C. And the difference is that we have different expressions for the bending moment. So what we do, we just first we do this cut and setting up the free body diagram for the span between 0 and A. And then we have this formula for the bending moment, it's awful formula. And then from A to A plus B to the right end, and we have something which is a bit more elegant, a bit shorter one. Then what we do, we have to integrate, and this is what Johnny actually wrote here. You have to integrate once to find the angle of rotation, and this is how it looks like for the section 1. And then you take the second integral, and you have this very ugly formula for the deflection. Then if you have a second section, again you do the angle of rotation, and you do the deflection. And then as you can see here, you have 6 unknowns. And then with these 6 unknowns, we do the 6 compatibility conditions, which are the displacement here is 0, the slope here is 0, the displacement here is 0, the displacement here is 0, and then you have continuity of angles here. So then you have all these 6 conditions, and then you solve 6 by 6, and you got the same result. So it's very sort of tedious. So I don't recommend to do it like this. It's way more practical just to take advantage of the existing knowledge and just take this sort of the guesses, not guesses, these results which were obtained beforehand using this method. So actually these things, just let me show, these things, they are obtained using this differential equation. But it has been done before and there is no point to do it again. Okay. So in principle, I'm afraid that this last slides, they are more sort of confusing than enlightening, because I think for you as a sort of it's the first touch of mechanics of materials, and then probably you are not going to be engineers responsible for the strength analysis. Then I think if you sort of kind of grasp this idea of superposition of standard cases, I think I will be happy. I think it will, from my viewpoint, it's sort of the aim of the course. Yeah. More questions? Oh, it seems you are completely exhausted. I'm sorry for that, but indeed this. So you see, this is how the timetable is organized. We have to finish this course and have exam on the 1st and 3rd March, and it means that we have to sort of to squeeze all these lectures in a very short time slot, and also have a lot of other commitments. So it was the only possibility for me to have this both morning and afternoon available for teaching, and that's why I gave these 2 lectures in one day. But I understand that it's quite tough. It's quite tough for you. And then remember that tomorrow we have to do one more lecture, the last lecture from my side, with a very typical name, fatigue. So I think you are sort of a bit of fed up with the mechanics of materials. So then tomorrow we'll talk about fatigue, but not in a humanistic viewpoint, but from the pure viewpoint of mechanics of materials. But before that, you are supposed to do the exercises. And then I think that the first 2 exercises are actually sort of presented in the lecture. So just sort of just give it a try, and then the last 2 exercises which deal with differential equations, yeah, probably you can skip them. So you just please sort of don't do the differential equation, only do the superposition. So then probably the problem 10.3.1, I think you can skip it, but try to solve the problem 10.4.3. Yes. Or at least take a look at the solution. Okay. Any questions? No questions. So then let's say until 3:30. I think I'll be available, and then I'll start preparing myself to this fatigue lecture tomorrow morning. So I'm online until 3:30. You're most welcome to ask questions or whatever, come up with the comments. I'm online until 3:30. Thank you.